In kinematics, we are going to deal with velocity vector also. And the first velocity was the average velocity, as you remember, we have defined in terms of the displacement and time. So this is the definition, and this is delta r, which is the displacement. In order to define the average velocity, remember, we needed at least 2 points in space. So these 2 points, for example, maybe P1 and P2, and this is your coordinate system. In the coordinate in 2 dimension, we need extra axis, which we call y-axis, and this is x-axis. This is the origin. So in 2-dimensional motion, this line, the blue line, represents the trajectory of the motion. Okay, the trajectory means the object traverses this curve as time passes. But this curve in here is not in position time graph. It is in coordinate space. Okay? So in coordinate space, that means at a certain time the object passes from P1, it moves, and at a later time it passes from P2. And the recordings of times T1 and T2 are there. So if you want to calculate the average velocity vector, remember, this is a vector now, not like in one-dimensional problems. The velocity is a vector. It is on the line connecting P1 and P2 and directed toward the final position, its direction. So this will be the green arrow line will be your average velocity vector. And this delta r, as you see, is a parallel vector to the velocity vector by definition, because the definition, the average velocity is related to the displacement, right? And they have the same sign. The only factor is this denominator, which is the total time. If you divide the displacement by time, then you will get the average velocity vector. Okay, so this is the pictorial representation. Remember last time when we were talking about the vectors in 2 dimension, I introduced the unit vectors, right? The unit vectors are 2 independent vectors. They are on parallel to the x-axis and y-axis, and we usually denote these vectors x hat and y hat. Most of the time, sometimes you see in the textbooks these unit vectors in x is represented by I, small I with hat, and the unit vector in y is shown as j. They are exactly the same things, okay? This is just a representation. If you see, I think in your quizzes, in your next quiz, you will see some problems. The vectors are given with this representation, I and j. Whenever you see I, that means the unit vector in the x direction, and j is the unit vector in y direction. So let's look at this example to calculate the velocity vector, the average velocity vector. And the question gives the object at initial position Ri 2 meters in the x direction and 3.5 meters in the y direction. And it says 3 seconds later, the object finds itself at another point, the final position, minus 3 meters in the x direction and 5.5 meters in the y direction. So the problem is, what is its average velocity vector? Okay, so if you go by the definition, everything is straightforward. Just subtract the initial position from the final position, Rf minus Ri, and you will do this in component wise. The x component will be minus 3 minus 2 meters, so it will be minus 5. Okay, and you will do the same for y component. 5.5 minus 2.5 makes 2 meters. And you divide this by a scalar. It's the time measurement, and it's 3 seconds. If you do this and also put the units in correct positions, you will get this velocity vector, average velocity vector. It is minus 1.67 in the x direction, meter per second, and 0.66 meter per second in the y direction. If the problem asks you, what about the speed of the object, then you will find the magnitude of this vector. So how do you find the magnitude of the vector? You just take the square of each component and add them and take the square root at the end. This will be the magnitude, and in the case of velocity, the magnitude is nothing but the speed, and the speed always a positive quantity. And if the problem also asks what is the direction of the velocity vector, what you do is you will calculate this expression. The direction is nothing but the angle of the velocity vector between the velocity vector and the x-axis. And this is done by taking the inverse tangent of the y component of the velocity vector divided by the x component of the velocity vector. Okay? And this will give you a minus angle. If you add this 180 degrees, you will find the correct answer. Okay? All right. So again, when we come back to the trajectory of the object in the coordinate space, remember always, if you see x and y, this is not a position time graph, it is a coordinate space. And in the coordinate space, the curve always defines the object's trajectory. Okay? That means object traverses every point, each and every point of this curve along the motion. So at any point on this curve, at any point, the velocity vector at that point will always be tangent to the curve. Okay? For example, here you see at this point the velocity vector is this green arrowed line, and it is, as you see, tangent to the curve. If I ask you what is the tangent vector at, let's say, this point, and what you do is you have no idea about the length of the arrow because you don't know, just by looking at the picture you cannot get the information about the speed or the magnitude or the length of the vector, but you can immediately tell its direction. Okay? Its direction will be a parallel line, a tangent line to the curve at this point. Okay? So this is the velocity vector, how the velocity vector look like at another point. It is always tangent to the curve, but you don't know about the length of the vector. For this you need extra information. So the next vector in kinematics is acceleration vector, and let's first talk about the average acceleration. As you remember from the definition, the acceleration is nothing but the change in the velocity vector. Okay? If there is a change either in the direction or both direction and the magnitude, then you have a non-zero acceleration. Again, let's look at the trajectory in the coordinate space. This blue line again represents the trajectory, and the question is, what is the average acceleration between these 2 points, this first one and the second one? Okay? For this, you will do some geometrical operations. First, you have to be given the length or the speed of the velocity at this initial position, and you just draw a tangent line to the trajectory at this point. This will be your initial velocity vector. And come to this point, the second point, draw another tangent line at this point with the appropriate length as you are given the value of the velocity. And you carry this second velocity vector without changing its direction to the initial point, okay? This vector and this vector are exactly the same vector, okay? Because it didn't change the magnitude, the length, also its direction. If the both directions and the magnitudes are the same, these vectors are equivalent to each other. So you can carry any vector in the coordinate space to any position without changing its direction and the magnitude. So these two vectors are the initial velocity vector and the final velocity vector. The problem is, what is the acceleration? The acceleration is just v final minus v initial, but you know how to calculate this. Just connect these endpoints of these vectors vi and v final, and the direction must be towards the final vector, okay? So the direction is toward v final. This is delta v, change in the velocity, of course vector. And if you divide this by delta t is the time it takes from going from one point to another point. These points, this one and this one.
Excuse me.
Yes.
Wasn't it same as average velocity formula? Same thing?
No, average velocity is different. Average velocity, you deal with the displacement vectors, final and initial position. In here, you deal with the velocity vectors. Okay. The formula looks like the same, but exactly they are not the same. In here, the change is in between the velocity vectors, not the position. In average velocity, we are dealing with the position vectors. So I divide this by the delta t, total time, you get the magnitude also of the average acceleration. So this purple line will be exactly in the same direction as the delta v, but its magnitude will be different because you divide delta v by delta t. So it's a different length quantity. And this purple vector is just the average acceleration between these 2 points, okay? It's not acceleration at this point, it's not the acceleration at the other point, but the average acceleration. If we are dealing with the instantaneous acceleration, that's a different story. At every point on the trajectory, again this blue line represents the trajectory of the motion of the object. At every point, you can draw instantaneous velocity and the instantaneous acceleration. For example, at point 1, of course, all the time, as I said before, the instantaneous velocity vectors are always tangent to the trajectory, okay? Look at this. At point 1, the green vector, the velocity vector, instantaneous velocity vector, is tangent to the blue line. Again, at second point here, the green vector is tangent. And here, it is tangent. However, when it comes to acceleration vectors, the acceleration vectors can be in any direction. Okay? They don't need to be parallel to the trajectory. Okay? Because it represents the change in the velocity vector. For example, at point 1, the acceleration is exactly in the opposite direction. So you can tell whether this object at this point instantly decreases its speed or increases its speed. So the question is, does it increasing its speed or decreasing the speed at this first point? I'm asking. Birinci noktada hız artıyor mu azalıyor mu? Why? Because the acceleration vectors and the velocity vectors are opposite to each other, right? If the acceleration is in this direction, that means the velocity is changing in that direction, but this direction is the opposite direction of the motion of the object. So obviously the object decreases its speed. What about at the second point? Here.
Say
If the angle between the acceleration vector at that point, instantaneous, and the velocity vector is perpendicular to each other, the velocity can only change its direction, not the magnitude. Okay? Right at the second point, the acceleration vector is perpendicular to the velocity vector. What happens in there? The speed is not changing at that point, but the direction is changing. Okay? You can easily see this. Right after this point, if you draw a tangent line to the blue line, it will be another direction. It will be like this. So what happens in the second point? The object only changes the direction of the motion, but not the speed, because the acceleration and the velocity vectors are perpendicular to each other. Sorry. At this point, if I give this extra information, if they are perpendicular to each other, then the speed instantly, the speed does not change, but the direction of the velocity is changing. That means the object is turning. It's very obvious, right? From the graph, because it's curving in the upper direction. What happens in the third point is the same. If the acceleration vector and the velocity vector are perpendicular to each other, then instantly the object changes the direction of its motion, but the speed do not change. At the final point, does the speed of the object increasing or decreasing? It increases because the acceleration and the velocity vector are in the same direction. Remember, I last time also have given this another concept, deceleration, right? Deceleration happens when the acceleration and the velocity vectors are opposite to each other. But if they are parallel to each other, then we need acceleration, or the speed of the object is increasing. Any questions in here?
What happens on the third point? Is it the same with two points, second point?
Same with what?
Same,
Velocity or?
same with second point. Like 3 and second point are the same station.
What happens?
Motion changes the
Okay.
direction.
What happens in the second and the third point? Their direction of the velocity or motion changes, but their speed does not change. Okay, the object's speed at these 2 points does not change. Why? Because the acceleration vector is perpendicular to the velocity vector. Whenever this is true, we say only the direction of the motion changes, but the speed do not change, but instantly. Okay.
For example, there is a velocity here and acceleration here and velocity here too, and total speed is increased.
You cannot add acceleration and velocity vectors because they are different things. Okay. So, in this chapter, you have seen when we are talking about the physical quantities in more than one dimension, we need to use vectors, and I have defined how can we draw the displacement vectors, the acceleration vectors, the velocity vectors in coordinate space. So this finishes the third chapter, and the next chapter we are going to deal with the motion in 2 dimensions. The motion in 2 dimensions takes place in x and y coordinates. So again, in this chapter, let me start.
I didn't understand last part. Where
Let's talk about at the break, okay? I will show it to you. So our next chapter is the motion in 2 dimensions. And this time, remember, the second chapter dealt with the motion in 1 dimension only. So everything was on a line, and we usually call this line the x-axis. And we dealt with the acceleration, the initial velocity, acceleration, and everything. Remember, we had defined a special type of motion which we call the constant accelerated motion. And in the case of constant accelerated motion, remember, the position as a function of time was given by this formula. X is equal to the initial position in x plus the initial velocity in the x direction times t plus 1/2 ax, the acceleration in the x direction, times t squared. So this is the position expression for a constant accelerated motion. When we have a second dimension, y, what we have is a second position. Okay? To this, we only add the second position, y, and y0 plus v0, y. This time, we have 2 components of the velocity, because the motion takes place in 2 dimensions. So in 2 dimensions, vectors have 2 components. One is x component, the other is y component. So in the y component, we are using the y component of the velocity, okay? And plus y component of the acceleration, because acceleration and velocity are vectors now, and they have components. If you are talking about 2 dimension, they have 2 different components, and we characterize the motion, the position of the motion, by these 2 functions, the function of time. If you are interested in knowing the change in the velocity as a function of time, then this time we are going to use these expressions. In x, remember, x is equal to v0x, the initial velocity, plus the x component of the acceleration times t. If you need to find the y component of the velocity, you will use a different formula. What is different in here is just, instead of x component of the velocity, you're gonna use the y component of the velocity, initial velocity, and the y component of the acceleration. So in fact, you have 4 different parameters in here. 2 for the velocity, vx and vy, and 2 for the acceleration, ax and ay. Okay, you need to know all of these components if you want to find the position at any time at any axis. And these are, remember, the velocity as a function of position. There are no time dependence in here. And remember how we derived these expressions. If you have only information in the initial velocities and the components of the acceleration, and you don't need time if you know also the displacement in x and y. That's it. So, in fact, we also solved an example problem. Remember the deer hitting problem. You were traveling on a car, and in front of you, a deer appeared, and you had to stop the car to avoid the hitting the deer, so we had used these expressions. If you look at back in the example. So let's do an example in two-dimensional motion. You are given the initial velocity of this bird, and the initial velocity is, as a vector, 4.6 meters per second. This y is the unit vector in the y direction. So immediately you can tell the initial velocity is in the direction of y because of this unit vector. And the problem also gives you the complete acceleration vector. And it is given 11 meter per second squared x unit vector. So you can always have the velocity and the acceleration vectors which are in different directions. Okay, you don't need to have all the time the velocity and the acceleration in the same direction, but they can be in any different direction. So if you are given this information, and this is a constant accelerated motion, obviously, because the acceleration does not change in time, it is constant, and there is no any time dependence in here. And initial velocity is given. The question is, what are x, y, the position in x, position in y, and the velocity at in x and the velocity component in y at a specific time given in here, 0.55 seconds. So at this time, what are these quantities? What you do is just use kinematics equation in x and y, put t is equal to 0.55 in here. So x0 is not given. That means the motion starts at the origin, so they are implicit information. You can take x0 and y0 as equal to 0. And the other rest are given in the problem, so just put this expression ax is 0, ay is 0, right? Because a is only in the x direction in here given. So this is also implicit. If you plug and chug x and y positions, you can find 1.7 meters and y as 2.5 meters. Also, you can calculate the velocity components in x and y components, y direction, by using these expressions. And Vx is 6.1 meter per second, and Vy is 4.6 meter per second. So a very straightforward problem. But the only thing is you need to be careful. You solve everything in component wise. You do everything in x, and you do everything in y differently. And then the problem also may ask you, what is the final speed of the bird at time t is equal to 0.55 seconds. So if you need to find the speed, then just you take the square of the velocity in x and y and take the square root. So Vx was 6.1 squared plus Vy is 4.6 squared, and calculate this to find the final speed, or the speed at time t is equal to 0.55 seconds. A very special motion in two dimension is the projectile motion. Okay? The projectile motion is nothing but on the surface of the earth. If you throw an object up in the air, that's the projectile motion. Or if you shoot your gun, the bullet moves in a projectile motion. Okay, that's why we call it projectile. What about the acceleration in the projectile motion? Do we have a horizontal acceleration on the surface of the earth? In the horizontal direction, do we have a acceleration? Do we have acceleration in the vertical direction? In the y direction? This is very easy if you think just throw in the vertical direction an object up in the air, observe its motion. If it changes its speed, then there is certainly acceleration in the vertical direction, right? But in the horizontal direction, there is no any force of gravity, right? There is nothing pulling or pushing you on the horizontal direction. So the type of motion in the horizontal direction on the surface of the Earth is a constant accelerated motion. There is no, constant velocity motion. There is no acceleration. Acceleration is zero. But in the vertical direction, we have a constant non-zero acceleration, which we call g. Okay? The constant acceleration of the Earth is called g, and it has a constant value, as I have given in my previous lectures. It is 9.81 meter per second square, and it is always downward, down to the Earth. Okay? But this concept of down, being down, depends on the choice of your coordinate system. I will talk about this. All right, so let's analyze then the formulas for projectile motion. Let's think about the horizontal component first. Since I have said there is no acceleration in the horizontal component, there is no AX. AX is zero. If you put AX is zero, and what you get in the X, in very general form, is this one. Okay? Just you need to know the initial velocity in the X direction, that's it. Or, in addition to that, you need to know the initial position, X0. But in the vertical direction, we have acceleration. And if you have chosen your coordinate system like this, if you have chosen the y, increasing y as upward, then AY is always minus g. Okay? But if you have chosen not this coordinate system, but this one, then AY is plus g. This is one of the main confusion about solving the problems in projectile motion. You be very careful in this, choosing your coordinate system. Once you fix your coordinate system, that choice of coordinate system fixes the sign of the acceleration. If you choose the vertical as the increasing y direction, then the acceleration is plus g. But if you choose upward as the increasing y direction, then AY is minus g. Okay? Once you fix this, everything is easy. And AX is always zero. So these are the most general expressions for describing the velocity and the position in projectile motion. You need to memorize these, okay? So what happens, velocity and acceleration vectors during the projectile motion, okay? If you throw an object from ground zero, from here, you can always choose the initial position as the origin. The trajectory of your object will be a parabola. Okay? This parabola, you know, in math, in calculus, parabola has this curved shape, and it is symmetric around this middle point, right? If you put a mirror at this point, it is symmetric in x. Along the x-axis, it's symmetric. If you, let's say, come from initial position to the top at a certain time, let's say delta t, from here to the ground, the same time, right? Also, if you shoot a movie of shooting the object in a trajectile motion, and if you reverse the movie, the motion of the object will be exactly the same, but in the opposite direction, just in x. But it's symmetric. All right. So what happens to the vectors then? Initially, of course, to have this trajectory, you have to give some initial speed, right? Without giving an initial speed, you cannot have this trajectory. So you need to give an initial speed. This initial velocity is called v0. See, v as a vector, v0. Since it's a vector, it has both the y component and the x component. These orange parts are just the components of the velocity vector, okay? Once you throw, what happens to the velocity vector or the components of the velocity vector? Does the x component of the velocity vector change during the motion? Just look at the picture. Is there any change in the x component of the velocity? If you start, you see, this is like this much, and after a later time, it's the same parallel vector. At here, it's the same, all the velocity is the vx now, and at here, it's the same length, and here, it's the same. The velocity vector in the x component doesn't change. Why? Because there is no acceleration in the x direction, right? Ax is 0. If the acceleration is 0, that means there is no change in the velocity, neither in direction nor in the speed. But what happens, the velocity vector in the y direction? You can tell me, is it decreasing or increasing? Initially, you have this orange, vertical orange vector. Later, you see the direction of the orange vector is the same, but it's shorter now. Right at the top, do we have any velocity in the x direction? The object momentarily does not have any velocity in the y direction at top. Okay? So at top, as you see in here, Vy is equal to 0. What happens after this? The direction of the velocity vector in the y direction, in the vertical direction, changes. Its direction was up during the motion until to the top, but after top, the direction reverses. That means the motion of the object is becoming downward in y. Does the speed in y increases? Just think about only the y component of the velocity. Is it increases or decreases? If I'm talking about the speed. Speed is increasing, right? You can tell by the picture. You look at the velocity vector at top, it's 0, but Vy is 0. I'm talking about Vy. But at a later time, you have a certain velocity in here, downward, and right at the hitting point, this is the largest. So that means the speed in the y direction increases. What about the speed in the y direction from here to here? From the initial position to the final, to the top. It decreases the speed. What about the velocity? It also decreases, right?
Yes.
All right. What about the acceleration vector right here? Tell me exactly the value, the component, the direction, everything. What is the acceleration vector at here? Who says down? Only one? Who says up? And the rest have no idea. The acceleration, once you fix your coordinate system, is always down at every instant of the motion. The acceleration is always this vector. At every instant of the motion, it does not change, it is constant, it is minus g if you have chosen this axis as upward axis as the increasing y. Okay. So at top, some of you might think that the acceleration is 0. But no. Acceleration is always minus g at every point. Okay, shall we give a break? Let's give a break and then 10 minutes.
Hocam, geçen paylaştığımız o modlarda şey yoktu herhalde. Örnekler yoktu.
Şey mi? Şu
Geçen ders yaptığımız.
geyik çarpıyor arabaya falan. Yok muydu? Evet. Koyalım şimdi. Koyarım. Bakayım. Bakalım şimdi hemen.
Yok diye gördüm ya.